and welcome to this. Just to note that all registrants will receive a copy of these slides and a link to listen back to the webinar, so note taking is optional. Today's webinar's topic is on using FMEDA to predict electronic design failure rates. And just if any questions, if people could kind of hold them to the end, but look, we'll work through it, don't worry. One of the most important but probably least looked at aspects of a new product design is component selection, especially in terms of effective useful life of the design. The perceived useful life depends on the industry or market the device is intended for. An example of this is an ARM microprocessor with a useful life of 3 years will probably far exceed the life of a modern mobile phone or tablet. However, the same device selected in the design of a new medical device will fail long before the product has an end-of-life notification. Just to say hi again, my name is Paddy Healy and I've come to exida after working as a clinical engineer for the Irish Health Service for 22 years. During my time there, I would have been on the other side of device failures, having to act on field safety alerts and work closely with medical device suppliers and manufacturers to try and implement solutions and fixes. The exciting part of my new role is that at exida, we work with product designers to ensure the product they design is safe and fit for purpose, and when it does fail, it fails in a predictable manner. So a little bit about exida. exida was founded in 2000 by several of the world's top reliability and safety experts. Professionals around the world turn to exida for help and guidance related to functional safety, alarm management, and industrial control systems cybersecurity services. exida has 3 business units. The Engineering Tools Division, we'll discuss a little bit more about that later on, the Certification and Assessment, the System Lifecycle Services. And these 3 units work well as part of the whole and are quite synergistic. The Engineering Tools Division design and develop a range of tools that make the process of functional safety and FMEDA somewhat easier and consistent. Integrated into these tools are exida's expert knowledge. This encodes decades of functional safety experience with common functional failure modes or deviations and diagnostics or mitigations. So the first tool that I'll just briefly mention is Excellencia, and this is a suite of tools, a bit like your Microsoft Office. It's a system engineering tool for supporting safety lifecycle tasks, streamlining the process safety management work process, and the safety instrumented system functional safety lifecycle. It also helps to streamline communication across an organization and between different departments when performing cyber risk assessments. And the other tool, the one we'll be using today in this webinar, is OEMX. This is also a suite of tools. It provides a common set to support hardware, software, and cybersecurity reliability and safety analysis for automation systems and critical safety devices. OEMX is comprised of 3 parts. RecX, which requirements entry and tracking, ArcX, which is for carrying out FMEAs, HAZOP and DFAs, and FMEDAX, which is the part we will use today. The software also includes exida's Component Reliability Database, or CRD, that incorporates over 350 billion hours of field failure data. exida develops analysis procedures and tools that help make functional safety compliance easier. All our methods and techniques are published and made available to the public, including our competitors. But before we move on, briefly mention what certification is and what it entails. Certification is a third-party authentication done against a set of requirements, which is called a scheme, based primarily on international standards. Systems, products, components, and personnel are getting certified. Functional safety certification involves a detailed analysis of both the engineering process and the design margins, resulting in random failure rate in all failure modes. And when applicable, cybersecurity certification involves a detailed analysis of the engineering process, cyber defense mechanisms, and network robustness. Basically, the earlier a problem or issue is found, the less of an impact it has on the cost. For example, making a change to a schematic in Altium or KiCad will cost time, but it can be absorbed. However, finding an issue when a product is out in the field will cost dearly, as every stage of the new product development is impacted. Many product design engineers do not consider how will a design fail. In today's webinar, we'll look at and answer the following topics. What is an FMEDA? We'll work through an example of an FMEDA, the requirements for a component database, the requirements for an FMEDA tool, and what is the FMEDAX tool from exida. Firstly, to mention an FMEA. This is a systematic technique that is designed to identify problems. It is a bottom-up method that starts with a detailed list of components in the system. The FMEDA analysis technique was developed in the late 1980s. The FMEA approach was extended to include an evaluation of the diagnostic ability of any automatic online diagnostic or manual proof test. We will further investigate an example FMEDA later. Remember, the FMEDA is intended to find design problems that can be avoided if we understand what happens when a component fails. The FMEDA, developed by engineers at exida by combining the part stress methodology with failure mode and effect analysis and adding in diagnostic analysis. When combined with a good component database, the FMEDA technique can predict circuit, module, unit, or system failure rates, failure modes, and diagnostic capability. FMEDAs have been shown to be quite effective in finding design errors also. An FMEDA done by exida will consider environmental factors, and we have presets to easily test the design. Each component in an FMEDA is looked at in terms of its failure modes, such as the component failing open, failing short, a change in its value by half or double, leakage, and for more complex components, shorts across the component package. Each safety standard operates with slightly different safety levels. For IEC 61508, these are referred to as safety integrity levels, SIL, ranging from SIL 1 to SIL 3. The automotive ISO 26262 standard uses the automotive safety integrity level, or ASIL, from ASIL A to ASIL D. To meet a certain SIL level, the failure in time fit rate must be below a given limit. The fit rate is the number of expected failures per 1 billion hours of operation, so a statistical representation for the probability of failure. The fit rate for any given component in a design is taken from the database and in exida's case the CRD, or Component Reliability Database. In addition to the fit rate, it is also necessary to evaluate and comply with the diagnostic coverage requirements. The diagnostic coverage is given as a percentage and describes how well the modules required for the safety features are monitored, and how reliably a fault can be detected. The coverage for any given type of diagnostic is defined as by the standard and can be low 60%, medium 90%, or high 99%. The higher the ASIL level, the higher the weighted average test coverage must be. The FMEDA analysis basically breaks down a design into 7 types of failure: safe, detected or undetected; dangerous, detected or undetected; enunciation, detected or undetected; and no effect or don't care. An FMEDA predicts the probability of a device failure due to a hardware failure. Done well, it can zero in on an exact component that will cause issues. A SIS, or Safety Instrumented System, is an implementation of one or more Safety Instrumented Functions, or SIF. A SIS is composed of any combination of sensor, logic solvers, and final elements. It usually has several safety functions with different safety integrity levels, so it is best to avoid describing it by a single SIL. In SIS applications, there are normally several important functions. Initiate a safety trip if programmed hazards are identified. Do not initiate a safety trip if programmed hazards are not identified, or perform automatic diagnostic functions to detect internal component failures. So function 1 is to initiate a safety trip if programmed hazards are identified. A failure to initiate a safety trip if these hazards are identified is called a fail danger or fail on demand. Function 2, do not initiate a safety trip if programmed hazards are not identified. A failure by initiating a safety trip if program hazards are not identified is called fail-safe. And function 3, to detect and enunciate internal failures. A failure of automatic diagnostics functions to detect internal component failures is called fail enunciation, because detected failures are not enunciated to the responsible repair personnel. The total lambda, or fits, is the sum of all these failures. The diagnostic capability of the equipment also impacts the PFD average, or the average probability of failure on demand, and the STR, the spurious trip rate. Diagnostic coverage can be measured. The variable is called C, or coverage factor. Coverage factors are often assigned to both safe and dangerous failure modes. When carrying out an FMEDA and working with a customer, it is important to ascertain from them what failure means to them and their product. These descriptions of failure can then be turned into metrics through the FMEDA process. What are the steps in an FMEDA? FMEDA is a predictive failure concept that can be used on brand new designs based on the design strength. It was derived because enough failure statistics at the product level had not yet happened. Neither manufacturers nor end users nor engineering companies do a really good job of gathering up failure statistics. And if they do, the statistics aren't available until the product is obsolete. Think about the usefulness of that. Therefore, given that we don't have enough failure statistics at the product level, where do we find these failure statistics? Well, at the component level. We break a design into its components and perform a detailed study of each component. It's truly a study of design strength. Every single part, it's reviewed. See if this part fails in a particular mode. If a capacitor fails, open circuit. How does that impact the design? Does the device continue to operate? Does the device fail? If it does it fail safe or does it fail dangerous? If it does fail in one of those modes, can the diagnostics detect that failure? Again, a well-done FMEDA would enable the system designer to zero in on a particular component that would reduce the reliability of the overall system. Using the component database that has failure rates, failure modes, and useful life, the FMEDA product generates a product failure rate as well as product failure modes, diagnostic coverages, and even useful life. Using a good component database, these numbers can be determined and predicted more accurately than with only manufacturers' field data on previous products. The FMEDA process can generate very detailed results that can clearly distinguish between different designs of mechanical, electronic, and electromechanical devices. To aid this webinar, we will look at an example product, carry out an FMEDA using the old spreadsheet method, and then carry it out using Exida's FMEDA-X tool. Obviously, our aim will be to get the same results, but hopefully show that the right tool can speed up the analysis process. So for this example, we will be looking at a simple flasher circuit. This is a modification of an annunciator circuit. The flasher will flash a light to indicate to a nearby person that a dangerous situation exists. The light intensity must be greater than 500 lumens. The flash rate will be roughly 1 per second with a duty cycle of roughly 50%. Other requirements stipulated are that the power supply must be 24 volt plus or minus 10%. A very important stipulation is that the circuit is designed to de-energize to trip. As the safety function requires energy, a diagnostic relay contact or solid state output will conduct if the power supply is available to supply power. If the power supply cannot power the LEDs, the diagnostic output shall no longer conduct. The next stage of the analysis process that we find helps significantly is to break the overall design down into functional blocks. For each block then, we can look at the inputs and outputs, and this will help with the FMEA. It also allows us to describe the deviations of possible failures within each block. Back to our flasher circuit, we can see that 24 volt is supplied to the main power supply, and this in turn supplies the required voltages throughout the rest of the circuit. The flasher input circuit shall detect if the input is 0 volts because a contact switch or relay has opened, or a solid state PLC current sink output stops conducting current. This is de-energized to trip, and will send a control signal to the LED flash circuit to flash. When the input is above 6 volts, the control signal to the LED flash circuit will indicate no flashing. The power diagnostic circuit shall detect if the power input falls below specification and signal the diagnostic output circuit. The diagnostic output shall provide 24 volts when no power failure detected, 0 volts if either power supply fails. Max current output is 20 milliamps, which is sufficient to operate a PLC input. When signaled to do so, the LED control will flash the LEDs once per second, and a duty cycle of flash shall be 50% plus or minus 20%. When supplied with a 24 volt DC, an array of LEDs wired in series shall generate at least 250 lumens of light when turned on by the LED flash control circuit. The next step of the FMEDA process is to look at each functional block and to see which components are part of which block. Whether we are using a simple spreadsheet or an FMEDA tool, This breaking the circuit down will help organise and lay out the FMEDA better. It will ensure no component is missed in the analysis. Something to keep in mind when doing the analysis and carrying out the FMEDA on a specific component. Only look at the effect of failure on that component for that block, not how it affects the entire schematic. For an analysis, we must have a basic understanding of how the circuit works. It is never a bad time to ask the designer if something is unclear, or sometimes components are used in unorthodox ways. For our flasher circuit, it is important to understand and remember that the enunciation is designed to de-energize the trip. Labeling the circuit is invaluable also, as it saves reanalyzing the circuit over and over. As we can see, and I'll show you now, we have labeled the circuit with key characteristics for each functional block. Here we have the 24-volt power with reverse polarity protection, the power loss detection circuit, which is comprised of a potential divider circuit. The output of voltage divider or potential divider is compared against a 10-volt reference. The op-amp comparator output goes to positive rail or 24 volts, switching the transistor on once we have a 24-volt power supply. Once the transistor is on, the optocoupler outputs low impedance. The PLC detects good signal from the power diagnostic. This in turn sends a signal of 24 volts to the connector J2, providing a good signal from the power diagnostic. The PLC, as we said, is programmed to de-energize the trip if it detects a dangerous condition. The LED flasher control enabled by disabling the optocoupler. This RC circuit, or the RC components here, fixes the oscillation frequency of this. The op-amp is configured as a Schmitt trigger oscillator. And these diodes are placed in the circuit to ensure constant current regardless of variations in voltage and temperature. For each functional block, we now look at the various failure modes and the impact they have. We need to distinguish safe from dangerous failures and figure out which failures are detected. It is not necessarily a bad thing to have failures in a circuit. It is how the circuit detects these failures and which state it defaults to. So doing a manual FMEDA on a component, we will use R6 as an example. This resistor is part of the LED flasher input subblock of the circuit. In our spreadsheet, we enter the parts and designations, the failure rate for the environment and application, the failure modes, we enter deviations and comments, we enter the effects, whether it's safe, dangerous, or enunciation or don't care, and we enter the failure per mode. But the big question we have to ask is, where do we get this data from? We reach for a component reliability database. For this design, the specification asks that it met Exida's profile tree. On analysis, it was noted that this component shouldn't exceed 10% of its power rating. The CRD categorizes this as low power, giving it a FITS of 0.6. The CRD then further breaks down this percentage of FITS value allocated to each failure mode for this component. The advantage, I suppose, of using a spreadsheet over pen and paper is the ability to plug formulas into cells. The cells from D3 to J6 over on the right-hand side of the Excel spreadsheet are populated with the relevant formula as outlined below here for dangerous detected, dangerous undetected, safe undetected, enunciation detected, enunciation undetected, and don't care. Cells B3 to C6 have the values taken from the database. So these lambda or FITS values are a percentage of the overall 0.6 FITS allocated to the resistor. All that is then required for us to do is to put in an A for enunciation, S for safe, or D for dangerous, or obviously hash for don't care into column A. And this will pre-populate the cells over on the right-hand side with the calculated values. Although it is a huge advantage using a spreadsheet over traditional pen and paper, as you can see, the resulting output is large and it is tedious work, repeating what we have done just for each component in the circuit. This is a relatively small circuit compared to many products out there on the market, approximately 30 components. So again, we can see the massive advantage using a software tool such as FMEDA for doing an FMEDA. But what are we missing so far? Proof test coverage, useful life, and what else? We'll come to that in a moment. The FMEDA methodology suffers from a potential flaw. The crucial factor to consider when doing an FMEDA is the component database. The database may be comprehensive but miss out on having important data, such as when the component is exposed to electronic stress. This will obviously increase the fits value, but if it is not accounted for in your database, then the analysis is incomplete. What if the wrong database or stress factors are selected in the FMEDA will not predict accurate results? I suppose the best analogy is garbage in, garbage out. So where does the component database come from? There are many general component databases available. When exida first started out, the databases available did not have all the components required for analysis. The failure modes were only included to a limited extent. There were no standard operating profiles. The IEC 62380 was probably the best available at the time, so exida started with this database and developed it. What makes exida's component database stand out is that it is a calibrated database. That is, it is compared to other sources, and when discrepancies occur, answers as to why are sought. Outputs from FMEDA are compared to field failure data, manufacturer data, SILSTAT, or EDA, to name a few. Most importantly, new devices and technologies are being developed every day, so the database must keep up. At exida, we gathered over 100 billion unit operating hours of field data, primarily from the process industry. We compare this field failure data results to the FMEDA results on a product level. We do it repeatedly, hundreds of times. Every time there is some fundamental difference between the field failure data, even manufacturer's field failure data, and when the FMEDA results, we must explain the differences. Sometimes we discover components have been used differently than we anticipated, and we add a new component to our component failure database. Sometimes we discover that the field failure data collection system had some fundamental flaw. We reanalyze the data based on excluding or including additional information. The key is, it's a closed-loop feedback system, which over time has developed a relatively accurate methodology for predicting future failure rates. So what's needed for a component database? We need, obviously, one that includes all components used in the design, realistic failure rates, component failure modes, failure mode distributions for each component, and useful life for various environmental profiles. So based on a foundation of IEC 62380, an electrical component database for FMEDA will need more information. Research to provide more complete failure modes, failure mode distributions, useful life for each component based on operational parameters, and new technology. Sources beyond IEC 62380 include internet research, component books, component manufacturer meetings, and field failure data. Over time, a lot of new components have been added to the database, especially small gate IC technology. This was done again by looking at field failure data. What sets the exida CRD apart is the multiple environmental operating profiles and the various stress uses for each component. To build a component database for mechanical components, no database at the component level was available. Component manufacturer meetings and field failure data were the primary sources. Again, for these mechanical components, operating profiles and application stress factors are selectable options. And what are operational profiles? These are a set of environmental variables. The CRD has profiles for subsea, offshore, cabinet, low power environments, and many others. As we can see from the example shown of the single operational amplifier, the fits varies from 4.6 to 18. These numbers depend on the profile selected that best matches the actual use case and the stress factor selected. The stress factor will normally relate to whether the component is used in a low power setting versus a setup closer to the component's maximum capabilities. But what about useful life? The useful life of a component, as mentioned before, is an extremely important factor to consider also. I know of one example where a medical device manufacturer was designing a new ECG recorder. This was on the back of a new component being released to simplify the design of biomedical devices. However, the new component hadn't got the same useful life figures as an instrumentation amplifier design used previously. However, the designers ignored the warning signs and punted for the more integrated, untested design. The product was a failure and lasted 3 years on the market before a new product had to be released. Because of this small decision, the medical device manufacturer lost huge market share and allowed its competitors to get a foothold. Useful life data is also relevant in terms of component selection, making sure that the design has components selected that should last the expected lifetime of the product, and that all the components closely match in life expectancy, or at least the lowest will last the expected product life cycle. There are several FMEDA tools on the market that typically do a much better job than a spreadsheet. We have discussed the key characteristics needed in an FMEDA tool. However, FMEDAX is updated one or more times per year with new components and new failure modes, failure mode distributions, useful life limits, and this allows engineers to stay up to date with new technology. The one we use at exida, like all tools, there's a learning curve, but here at exida we can provide introductory training, phone support, and complete customized training as required. Diagnostic coverage is integrated into FMEDAX by having a database of diagnostic techniques and expected diagnostic coverage factors for well-known techniques such as ECC memory tests, etc. Based on diagnostic coverage, these diagnostic coverage factors are based from IEC 61508, which is used as guidance. This final slide shows the output from our own FMEDA tool. Same results as the spreadsheet method, but in addition the tool can output a formatted results table, calculations for proof test coverage, and all other needed functional safety information. The tool allows the generation of nicely formatted reports for FMEA, FMEDA, and various other potentially required outputs. So I'd like to take this opportunity to thank everyone again for their time today, and I hope you found this webinar informative. If you still have questions or need more information, please check out the exida website, where you can find loads more webinars and lots of white papers on various different topics. As we said at the start, everyone will receive a copy of these slides. Thank you again for your time and attention, and if anyone has any questions, I'd be happy to try and answer them now.